Today we're going to go ahead and take a look at what happens as x goes towards infinity. In other words, when you're looking at your graph, what happens to your function as you go far to the right on your graph, and what happens to your function as you go far to the left on your graph. Sometimes your function will level out at a certain height as you go far to the right or far to the left. And in that case, you would have a horizontal asymptote of y equaling whatever the limit of that function would be. So we're going to look at limits as we approach infinity for x. So in other words, you're plugging in bigger and bigger numbers. If you plug in bigger and bigger numbers, well, for the most part, if you plug in really, really big numbers here, what we have going on is we have a big number to a power here minus still a big number, but not to a power. So this doesn't really do a whole lot when you're plugging in really big numbers, like something in the billions or trillions. Because if you take a billion cubed, that's going to have way more many zeros with it than this would. So what has most influence in the top is the biggest power. Well, same idea here. What would have the most influence in the bottom would also be the biggest power. So when you have a polynomial over a polynomial, meaning a rational function, you just look at biggest power over biggest power. And all you have to do is simplify that down. In this case, the x cubes drop, leaving you with just 3 over 2. So this function, when you would graph it, would level out at a height of y equals 3 over 2, that horizontal line. A problem like this here, we have a root minus a root. And you might think, oh, well, won't the roots cancel? Well, maybe. We're going to want to go ahead and try to do our conjugates. So we'll do the conjugate at the top, and if we multiply the top by the conjugate, we're going to multiply the bottom by that same conjugate. Remember, in FOILing out the tops, first terms. Remember, in doing conjugates, your outer terms and your inner terms cancel because the outer terms is positive, the inner terms is negative, so they cancel. Then you do your last terms. Negative root x times positive root x would be a negative x. The bottom is still just your conjugate. You'll notice on top here, your x's drop. One's positive, one's negative, so you just get this. So now we look at what we have here. Here we'd have one number on top. Over, if we're plugging in big numbers, so a is some number we don't know, but if you're plugging in big numbers down here, the square root of a big number plus the square root of another big number would be a big plus a big. Well, big plus big is still really big. So you get some number over something really big, meaning you'd be dividing by something really big, so it would end up being close to 0. So here, you still want to look at most influential over most influential. But you'd want to take what we have here in the bottom and FOIL that out. 1 plus e to the x times 1 plus e to the x. So if you write that out, 1 plus e to the x, 1 plus e to the x, you do your first terms, you do your outer terms, you do your inner terms. When you do your last terms, remember e to a power times e to a power, you'd have to add those exponents. So that's how we get this. And then you want to do biggest power on top, which there is only one power, over biggest power in the bottom, which would be this last thing right here. So you look at that, well, e to the 2x over e to the 2x cancels, so it's just 4. This problem over here on the right, we are multiplying a couple things together. But you notice this first thing has a negative exponent. Well, let's move this first thing here down to the bottom. And then it wouldn't be a negative exponent. And then we'd have this. Now, hopefully you remember that the sign of anything is always between 1 and negative 1. So now on this first part, you'd have 1 over something. You're plugging in big numbers, so this base would be big, raised to a big power. So you'd have something big raised to something really big, which really means it would be 1 over something extremely big. Well, 1 over something extremely big, you should know, is close to 0. So basically, you have 0 times something between 1 and negative 1. Well, 0 times anything is 0. Now here, technically speaking, you would probably have to go ahead and divide the top and the bottom by the square root of x squared. You'd have to divide the top and the bottom by that, or multiply the top and the bottom by this. Now, you could do that, and that's what a math professor in college would tell you to do, but, well, I think there's an easier way to look at it. Now, when we are looking at this, most influential on top over most influential on the bottom, well, on the bottom, that x comes out of the root because it's squared, and we'd have this. Huh. And you guys know that x over x cancels, so we should get 3 over 2. The question you want to double check yourself with is this. Remember, what side's in front here is really positive. So that means the whole bottom has to be positive. So to ensure that the bottom is positive, that x is technically an absolute value. So you know the whole bottom's always positive. It's not really that big of a deal here because when you look at what we're doing is we're plugging in a positive. So we know that this x is positive, this x is positive, so that means the absolute value doesn't do anything. So it really is what we had initially, and the x's do drop, and you get this. And so it is over this, which if you wanted, you could simplify that, get the root out of the bottom, and your limit would be this. Well, the problem on the right is really the same thing, except we're going towards negative infinity. So based on our work we did before, we know that what we're going to have over here is this. But now our x's aren't going to drop. We know that when we plug in a negative infinity, the top's going to be negative. But because of the absolute value here, we know it's going to be positive on the bottom. So we know we're going to then get a negative 3 square root of 2 over 2, because we would end up getting a 3 over a root 2, but one's positive, one's negative, so you know the whole thing's negative. A second way you could have thought of this is you could have thought, well, I would have this on top. If I put in a big negative here for x, if the inside's negative, it does the opposite of that. And now the x's would drop, and we would still get the exact same thing. So there's a couple ways you could think about that absolute value. What we did here initially or what we did here would not really make a difference. So here we're still looking at our limit as x approaches infinity. So we really have something really big, and we'd be cubing it. So if you have a big positive and you're cubing it, it's really, really big and still positive, because a positive cubed is a positive. So in other words, as you go far to your right on your graph, your function would continue to increase without bound. In other words, it would continue to go up towards infinity. So technically speaking, your limit does not exist, but you could put down that your limit would diverge So we put an arrow to positive infinity. If it converges, it approaches a certain number, and we would put an equal sign instead of an arrow. But if it does not approach a particular number, and remember infinities are concepts, not numbers, then we would put arrows. So over here on the right, we're plugging in a big negative. So a big negative cubed, well, you should remember a big cubed is big, and a negative cubed is a negative. So we get a really big negative number. In other words, as you go far to the left on your graph goes down forever. So in other words, your limit here would diverge to negative infinity. So here we have a polynomial over a polynomial, which is a rational function. What we're going to have to do is we're going to realize that there would be no horizontal asymptote because the top would get bigger than the bottom. So technically there would be no limit, but we can still go ahead and figure out what's going on. If the top has a higher power than the bottom, we're going to have what we call an oblique asymptote, which is a line or a curve that your graph gets close to but never touches as you go out to the infinities. Well, when the top is a bigger power than the bottom, all you really have to do is longhand division. So you can do longhand division, or in this particular case, because you're dividing by x plus a number or x minus a number, you could do synthetic. But longhand division will always work. If you did synthetic or longhand division on this, then you would get your quotient to be this. You would get a remainder, and that's okay. Divided by, or over your divisor, which is x plus 1. Well, we're looking at what happens to this graph as you go far to the right. Well, if I go far to the right, 6 over, then it would be something big because you're plugging in infinity. 6 over something really big would really be close to 0. So your graph really just gets close to this diagonal line. That's your oblique asymptote. Now, technically speaking, your limit would be slightly different than that because your limit would be what you get when you put in something big here, can't do there, something here. If you plug in something big there, you get 2 times big minus 6 plus 6 over big, which would be 2 times big minus 6 plus 0. Well, it would be really big after you double it. Minus 6 would still be big. So in other words, technically your limit, we would say, is positive infinity. However, we could use this whole idea right here of knowing what line we get close to as we go far to the right on your graph. Now, that y equals 2x minus 6, once again, is your oblique asymptote. That's the curve that your graph gets close to as you go far to the right and far to the left. Now over here, technically we're putting in a big negative here and a big negative here. So you'd have 2 times a big but negative minus a 6 plus a 6 over something a big negative. Well, this last part here goes to 0. So this would be a negative 2 times something really big. It's a negative 2 because a negative times a positive, you know, is negative. Well, a negative times a big is negative, minus something is really a big negative. So it's going towards negative infinity. So we would put an arrow and put down negative infinity for your limit. It does not exist because it does not approach one number. It only diverges towards infinity.